Okay. Nee, is niet goed. Ja, het ziet er goed uit. Oké, start recording. Yeah, the time. Okay, so we're back. This is a second part of lecture 12, which is the last lecture in multibody dynamics in this course. Yeah, I hesitated a little bit before the break when I was talking about this calculation. I started with 2 bodies because you clearly see 2 bodies, and then I thought, oh, it doesn't add up, and it's of course 3 bodies. Now, why 3 bodies? I was not clear about that. Well, it has to do that I decided to use just 3 hinges, and when you use 3 hinges, then actually what you have to do is you have a disk, with 1 hinge, then the second hinge goes to some virtual body here, and then from that virtual body the third hinge goes to the third real body. So this is the third body actually, the kind of a virtual body. So that is a way. Another way of calculating would be, no, we don't do virtual bodies, bogus. So that is the way how this goes. You could also say, no, I take here a 1 hinge, and then I take this set of 2 hinges, and then I take my second body. But then the constraints are a bit different. Then we have 2 times 6 for the coordinates, which is 12. And we have 1 hinge here, which is 5 constraints. And then here we have another hinge, which is only 4 constraints, because 2 motions remain. So we have 5 plus 4 is 9, and then we have 3 degrees of freedom. So that was a bit unclear when I started the lecture on calculating degrees of freedom. This is the approach we usually take in multibody dynamics A, where we use with the Atom software and so on. And this is usually the approach we take in an more analytical way for the DAE. Okay, but we're not doing DAE, we're doing TMT. And then before the break we finish with this beautiful equation of motion, right? So m times q double dot is forces, and of course maybe it sort of helps if you say, well, these are a function of q and q dot, and they're even quadratic in this one. And of course then the applied forces, that you see that they're from q dot, and you see that everywhere. And from q you see the transformations in here. Anyway, it always breaks down, of course, to forces mass times acceleration. There's nothing new there. The first part, these transformation matrices for coordinates, is pretty straightforward to do, so I will not dwell into that. More complex is how does it work with the angular accelerations, which was also the topic of our homework assignment 11, right? And also of 12 now, the one to come. And let's dwell into how do we get this expression of the angular velocity in terms of our generalized coordinates and speeds. So that is the goal for now. So what do we need in the end? Well, we need, for every body, we need some expression of omega. This is then the omega of body 1 in its own coordinate system. And for this body we also need an expression for omega of body 2 in its local frame. And the big question is, we have to express those in terms of q and q dot. And how do we do that? And the same for this one, express them in q and in q dot. And how do we do that? We've seen it's linear in the velocities, but it's absolutely non-linear in those ones. Okay, how do we proceed with that? Well, first of all, we identify that for angular speeds, if these are the generalized coordinates, we can write these as also as vectors, right? We don't say in which coordinate system, but we say, oh, there's a vector omega alpha here. And likewise, around this axis, there's here a omega beta. And around this axis, there's a omega gamma vector. And then, if you want to calculate what is the angular velocity of this disk, then without going into which coordinate system, I can say, well, the omega of this disk 1 is just omega alpha. And likewise, I can say, oh, the omega of this one, of body 2, well, I don't know in the coordinate system, but I do know it is a chain, and it starts with this angular velocity, then this angular velocity, then this angular velocity. So you have to add up omega alpha plus the omega beta plus the omega gamma. Now, that is sort of helpful. What do you know about these ones? Well, this one, the axis is constant, so we know about this omega alpha that if we express it in this inertial frame, or even if we express it in body fixed frame of 1, then it should be a rotation about the z-axis, alpha dot. Those are the components. So, and the funny thing is, of course, this inertial frame and this B1 frame, the rotation is about this axis, so everything about this axis stays the same, so therefore these components are identical. Okay, so that is for the alpha. Then about the beta, that's a bit more complex because that has to do also with this rotation. So what do we know about the omega beta? Well, we know that the omega beta expressed in which coordinate system? In B1 is equal to, well, it's a rotation about the y-axis initially, right? So it's a 0 beta dot 0. And then finally, what do we know about the omega gamma? Well, we know the omega gamma is of course in this B2 system and in this intermediate system, which is identical of course, but we know the omega gamma components in the B2 system are, and it's a rotation about the minus x-axis, so it's minus gamma dot 0, 0. So we see that we know all these various angular velocities in different coordinate systems, and in the end, what do we want to know? Well, we want to know them in their own body fixed frame. And I think that's the biggest trouble you have. So the omega prime 1 is actually the omega 1 in B1. But that's super simple because that's the one we already have directly. So that's 0, 0, alpha dot. That's simple. So that's solved for omega 1. But now omega 2. So omega 2 prime, and we want to have the omega 2 in our B2 frame, is, well, the easiest way is to walk backwards and start here and then go backwards. So I need a little bit more space, so I start at the end. Why do I start at the end? Well, because the last rotation is already in this frame, this gamma dot. So this vector is already good. So that is just the minus gamma dot 0, 0. Then the beta is actually, that's in the B1 frame. And I don't want to be the B1 frame, I want to have it in a B2 frame. So what is the difference between the B1 and the B2 frame? That is a transformation. And which transformation? Well, the beta doesn't matter because that's the identical one. It's identical for both frames, for B1 and for this intermediate frame. The only one is the gamma. And I have to go back to my coordinate system, so I have to do a backward rotation. So I need the rotation matrix of gamma and then transformed to get this rotation back into this frame. This rotational is, there's this axis in between, and that's the gamma, and I have to go back to my frame, not from my frame to the wall, but back, and therefore I have to transpose. And then finally, I need a little bit more space. Oop, 100%. So this, we move a little bit to the side, yeah. And then finally I need the alpha. Now, what do I know about the alpha? I know the omega alpha in the B1 frame. So then I have to go back and then look at the picture. I know this one, and then I have to go back through these two hinges to this frame. So, well, the alpha doesn't matter, but the beta and the gamma does. And since I have to go back, yeah, I need that reverse order. So R beta transpose R gamma transpose. And that brings my my omega alpha back to my body 2 frame. Now, of course, we can write down this R gamma transpose, R beta transpose, and I like to just write out the components 0, 0, alpha dot. Then we get this rotation matrix, and the beta was around the middle axis, right? What was the beta? Yeah, middle axis, so that was 0, beta dot 0, and then of course the last one is just the same, 0, 0. So in conclusion, this is our omega 2 prime, and as you can see, of course, linear in the speeds, in the time derivatives of these generalized coordinates. Now I'm going to write everything in terms of these linear matrices. So I'm going to write omega 2 prime is some matrix, yeah, and I'm going to give it a name B2. What did I do? B2. I call it B2. It's a function, of course, from alpha, beta, and gamma with cosines and sines. And then here on the right hand side I have alpha dot, beta dot, and gamma dot. And note the order. Note the different orders. So between those and this guy. Because again, these time derivatives are no vectors, and this is a real vector, this is also a vector, but this is just an ordered set of our components, right? Yeah, that having said, then it's not only the angular velocities we need, we also need the angular accelerations. Bugger all. So I have to differentiate this. Omega dot 2 prime is, well, that's simple. We keep this constant, that's the B2 times, and then I write here Q dot for easiness, and then I get the B2 comma Q double dot, sorry, Q dot. And again, I write B2 Q double dot, and I name this G. Oh yeah, the G terms, G2. So these are convective terms. Okay, now I'm actually all set, and of course I have to do the same for body 1, and you get the same sort of expression. And then in doing that, I then can finally get to my equation of motion. Yeah. And let's see if we have covered all the elements. Yes, because we have covered these transformation matrices, we have covered these, that's the one we went into all this trouble down here to find out what are all these linear mappings. We found those. Here they are already known. These convective terms we have done from those. Then these convective terms we have done down there, and the B we already found. So it's just then bookkeeping, getting everything together, and finally expressing everything in your generalized coordinates. And so that is in a nutshell how you treat such a problem. Now, maybe you think, oh, and for other problems, how does that work with different constraints? Well, if you have sliding joints or other type of joints, well, then you have to formulate the type of joint you have. Either if you do independent coordinates, then you have to see how the chain of degrees of freedom is. If it's a closed loop, you have to formulate that closed loop. Maybe there's like a line here that's constant. I don't know. You can think of a number of constraints which you can add to the system, or more bodies. Just add them, just formulate them, but in essence that's the way. So that was the way for the TMT. The DAE I already discussed in the beginning, and then the Lagrange. Well, the Lagrange is goes a bit like this, because in the Lagrange equation you also have to formulate what are my angular velocities. You need that because you need to determine what is the kinetic energy of the body. So what are my angular velocities in terms of my coordinates and my speeds. Then you put everything in, add it up, and then you have to differentiate again, and those become very lengthy and unmanageable expressions. Whereas in this case, with the TMT method, you can do it easy on a body-by-body approach, which makes all the contributions more manageable. You can even you never do this symbolically completely. The sub-matrices you always do symbolically, because you don't want to make any errors, but then you make it numerically, so you just numerically in every position calculate what these matrices are, and then you do the multiplication, and then you do not get an explosion of terms, and everything is restricted to just numerical calculation. Now, why don't we do everything symbolically? Why do we do only these symbolically and for the rest not? And I have a small example on that. Let's presume you have two variables, a and b, and they are symbolic. So you have a and b. And then you want to calculate c as being a plus b squared, right? Okay, now are two approaches. If you do it symbolically, then what do you get? Well, then you get a squared plus 2 times a times b plus b squared, right? If you do it numerically, what do you get? Well, you get an intermediate term is a plus b, and c then becomes t squared. Now let's calculate how many multiplications and how many additions do we have. So multiplication, it's 1, 2, 3, 4 multiplications, so 4m plus 1 plus 2 additions, right? 2 additions. What do we get here? We have 1 addition plus 1 multiplication. And this clearly shows the explosion of terms. So this is already for a very simple symbolic thing. The moment it becomes more complex, this is really horrendous what you get. A big tree which cannot be simplified, whereas in the numeric case the number of operations really get reduced. So never ever expand everything symbolically and then try to solve it. Okay, then I like to finish by saying thank you. Thank you for all your effort and your enthusiasm in the course, and your dedication also for doing the homework and doing the peer grade. I was very, very happy with how the peer grade system went. I hope it also helped you in learning the material in the course. And then finally we have our digital exam, digital exam for the course, and that's on Friday the 3rd of July from 9 to 12. And since we still have corona measures, this will not be at the university, but it will probably at your own local place, but you will get enough information on that. You can easily prepare for that. There's an example digital exam problem is there on Brightspace, and look it up, see how it goes. Then you have an idea how the exam problems go and what is expected of you. It's a fully open book exam. You can use all your material, all your MATLAB files, the book, everything. It's totally open book, and it's three problems which are close to the homework problems which you then have to solve. Okay, that having said, I think I have covered everything. There is a question in I see in the chat, but I propose that if you want to have an answer, then go away. If you want to have an answer, then please go to to the questions and answer after lectures Q&A, which I will open in a second. So yeah, I'll sign off for now. Thanks again, and I see you all at the exam. Keep up the good work.